In previous lectures, we developed a framework founded on Newton's second law for proceeding from observing motion of our system to solving for specific interactions of the surroundings with the system. To apply this framework, we begin by identifying the system whose motion we're studying. Then we observe the system motion to determine the net force, F net. At this step, we fleshed out how to describe observations in terms of the change in momentum over the change in time, specifically by thinking about those changes in separate parts. One part of the changes parallel to the system's motion, changes that are non-zero when the system speeds up or slows down, and the other part of the changes perpendicular to the system's motion, changes that are non-zero when the trajectory of the system is curving. These observed changes, if present, must have a cause. Newton's second law tells us the total interactions are the cause. And, moreover, if they're speeding up or slowing down, there must be non-zero total interactions causing that. And if there's curving to the system's trajectory, there must be non-zero total interactions causing that. Observations of the system's motion tells us all this, even when we don't know what agents in the surroundings are doing the pushing and pulling. However, if we can identify these agents, then often we can solve for one or more of the interactions, the forces associated with these agents. Today we'll illustrate this process with some examples. As a warm-up, let's consider the motion of this presently unknown object, whose trajectory, whose path in space we observe to be like this. The object is moving in the direction indicated by the arrows, and the position of the object is shown for a particular instant in time. At this instant, which of these statements about the net force is true? The correct answer is the net force is non-zero. We learn this from observing the motion and applying Newton's second law. We see the path of the object is curving. This means delta p over delta t perpendicular is non-zero. We can even visualize delta p over delta t perpendicular here by recognizing the kissing circle, the circle that smoothly fits the trajectory at this instant, must look something like this. As we know, the direction of delta p over delta t perpendicular must be toward the center of this circle. By Newton's second law, there must be a cause for this curving. There must be non-zero total interactions, F net perpendicular, pointing in the same direction. So, if at least F net perpendicular is non-zero, then F net itself must be non-zero. Let's push this example one step further. Let's say at this instant we also observe the object is slowing down. Which of these arrows best represents the direction of F net? To answer this, we first need to determine the direction of F net parallel here. Again, from the observation, here from delta p over delta t parallel, which, as we said earlier, points opposite to the direction of the object's motion if the object is slowing down. By Newton's second law, there must be a cause for this slowing down. There must be non-zero total interactions, F net parallel, pointing in the same direction. Putting all this together, we know that F net perpendicular points toward the center of the kissing circle, and F net parallel must point something like this, so F net, which is the vector sum of these, must point something like this. So this is the correct choice. Notice we learn all this about F net without knowing what in the surroundings is doing the pushing and pulling. Now, if we do have that kind of information, we can go further. So, for example, if our object is a comet that is interacting gravitationally with a star, then we could connect what we learned about F net parallel and F net perpendicular to what we know about the gravitational interactions from Newton's law of universal gravitation. We'll say more about how to do that later when we prepare for our upcoming lab that connects the motion of a star to gravitational interaction with a black hole. For now, let's look at this observation of motion involving the physics of extreme sports that use ropes. We're going to build and to analyze a simplified model describing the motion of the climber on this amazing rope swing. Let's say the climber has a mass of 90 kilograms and is swinging on the end of a rope 45 meters in length. At the instant we show here, we observe the climber is moving on the downswing with a speed of 11 meters per second. At this moment, the angle between the rope and the vertical is 30 degrees. What's the tension force exerted on the climber by the rope? We start with our fundamental principle, and we take our system as the climber. Our observations tell us a lot about F net. The climber is on the downswing, so we observe the climber is speeding up. Therefore, delta P over delta T parallel is non-zero and points in the direction of the climber's motion. And by Newton's second law, a non-zero F net parallel must be the cause, must point in the same direction. The climber's trajectory is curving as well, so delta P over delta T perpendicular is non-zero, and therefore F net perpendicular is non-zero too. We can make a stronger statement about these if we assume the rope remains taut and at a constant length. Then the climber's trajectory is a circle. In fact, it's the kissing circle. So then we can say something about the magnitude of delta P over delta T perpendicular, which, by Newton's second law, must be equal to the magnitude of F net perpendicular. We know all these quantities, so we can solve for this. We'll do that in a moment. We're now ready to move to the next step. Let's start with agents in the surroundings exerting contact forces. Here we have just one. The rope exerts a tension force acting on the climber. We're going to ignore the drag force due to the air in contact with the climber here. We have one agent in the surroundings, the Earth, exerting a non-contact interaction, a weight force. Let's show all these on a free body diagram. Let's also choose our coordinate system here. Let's place the origin at the climber and choose the axes oriented in the parallel and perpendicular directions, with the positive parallel direction pointing in the direction of the climber's motion, and the positive perpendicular direction in the direction toward the center of the kissing circle, toward the attachment point of the rope. Remember, we're free to choose our axes' directions, labels, and orientations as we like. We're making choices here that help us solve our problem more easily because we notice, with this choice, the tension force, which is the unknown we're trying to solve, has only one component in this coordinate system, the perpendicular component, so we can focus on just that component. The sum of the forces along this component direction, F net perpendicular, will include both the tension force and the component of the weight force along the perpendicular direction as well. Notice the tension force component is positive, points toward the center of the kissing circle, but the weight force component is negative. Using trig, we can write the weight force component with the correct magnitude and sign like this. Now, from observing the motion, we know both the magnitude and the direction of F net perpendicular. So we have only one unknown, the tension force, so we can solve for that. We can summarize this result by saying the tension force has to be larger than the weight component along the perpendicular direction because it has to be larger by just the right amount to give the F net perpendicular needed to cause the climber's trajectory to curve in just the way we observe. We can find other unknowns in this problem as well. For example, we can solve for F net parallel. From the free body diagram, we see that only the weight force component along the parallel direction contributes to F net parallel. So we can solve for that. Now we have both F net parallel and F net perpendicular, and so we know everything about the net force just from observing the motion. As a final note, we need to point out that our model will need to be improved to describe a real rope swing because the climber's true trajectory won't be a nice circle. This is so because the length of the rope does change because real climbing ropes stretch by a significant amount. This makes sense because, as we remember, at the microscopic level, tension is due to the stretching of chemical bonds that we can think of as spring-like forces. So in effect, Real ropes have a spring-like character that we would need to account for if we want to build a realistic model of how ropes behave in sports like rock climbing or bungee jumping. We'll talk about how to add that spring-like character in a later lecture.